Warning! The video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This is part 4 of a series on graphing using calculus. And again, we still have not included oblique asymptotes, and we have not included symmetry, not yet. We're just not to that point yet. We still need to introduce something called L'Hopital's rule, so that'll happen in a little bit. But here is the how-to. I've already said it in the previous video, so I'm just going to move forward right now into the actual problem at hand. In this problem, we're being asked to graph f of x is equal to x squared e to the 5x, where our domain has been restricted. It's artificially restricted to go from -5 to +5 with inclusion at the endpoints. So immediately, they've already handed us the domain. So I'm just going to write that off to the side that our domain is a beautiful -5 to 5. So I'll just put that in brackets here, -5 to +5. And now I'll go through with my old school algebra. This is actually not going to be too bad, right? So the y-intercept here, you let x equal 0, and you'll get 0. The x-intercept, or x-intercepts if you have more than one, you would solve 0 is equal to x squared e to the 5x. Well, we happen to know e to the 5x is never 0, so you could divide both sides by that, and you would end up with the fact that x would have to be 0, and we already have that. So my x-intercept is 0, 0. It's the same as my y-intercept. Now that I have a point, though, I'll go ahead and start building a table off to the side. Just keep my information kind of cleanly gathered. All right, let's go through. Let's see what else. So we did our Algebra 1 stuff, the intercepts. We also did our Algebra 2 stuff, which is finding the domain of the function. Let's see, what else can we do from algebra? Domain, Well, I guess we're just going to go into pre-calculus. Let's go ahead and talk about vertical asymptotes. Well, if you take a look at the function, there's no domain restriction other than the artificial restriction they've given me. But otherwise, this function would never have a division by 0, or it doesn't have a natural log or a tangent or something like that. So there's no domain issues otherwise. That means there's no vertical asymptotes. So vertical asymptotes in this case just do not exist, or there's none. Same thing with the horizontal asymptotes, because again, we have a limited domain. Horizontal asymptotes are all about the end behavior of a function. Well, this function's not going off to infinity or negative infinity, so we don't have to worry about that either. So this problem looks like it's going to be a very fast problem because we've already rocketed through most of the material that we are asked to find when we're graphing a curve using calculus. Now we start actually using calculus. Let's go ahead and take the first derivative. So f prime of x, and the purpose of taking the first derivative is because you want to find the critical numbers of f. So we're finding the critical numbers right now. And the critical numbers of a function occur when that function's derivative is 0 or it doesn't exist. So let's go ahead and take a look at the derivative. It's a product rule. So that'd be 2x e to the 5x plus 5x squared e to the 5x, because the derivative of e to the 5x is 5e to the 5x. And this I would highly recommend factoring. That'd be e to the 5x. Actually, technically, you could factor out an x as well. Do I want to? Yeah, I'll do that just for the purpose of evaluating it. I'll get 2 plus 5x here. That's left in there. And we want to know when this does not exist, which it exists everywhere because it's an exponential times a polynomial, and both of those exist everywhere. So this exists everywhere in the domain. Now we just want to know, when is f prime equal to 0? Well, f prime is equal to 0 when x is 0, or when x is negative 2/5. So this gives us a nice critical number other than 0. So I'm going to go ahead and graph really quickly, scratch this out, graph out a number line. Remember, our domain goes from -5 to +5. So I'm really not worried about anything other than numbers between -5 and +5. We know that we have a critical number at 0. And we also know that we have a critical number at negative 2/5. That's going to be kind of a pain, but what are you going to do about that, right? And remember, this number line represents f prime. All right, so we need some points to test each of these pieces of this interval. We have 3 intervals here. I'll just go from left to right. So let's take a look at f prime of -4. That might be the easiest to start with. So I'm going to be looking this entire time at the factored form. Factoring is really nice because it allows you to quickly evaluate a function. So I'll look at the factored form the entire time. And I'll also note that the exponential part of the factored form is always positive. So I don't really care about that. That's not a concern for me. What is a concern is the stuff that's not in the exponential function. So f prime of -4, well, that would be a negative number because it's -4 times 2 plus 5 times a -4, which is -20. So that's another negative number. And so you have 2 negatives multiplying. It's going to be positive there, which implies our function is going to be increasing on that part of the interval. Now, the next part you're going to have to test is between -2/5 and 0. Obviously, -1/5 is probably a good choice. Again, I'm going to plug that into the derivative, specifically this highlighted portion, and I won't care about that e to the power, because again, that's positive. So f prime, let me write it in black below, f prime evaluated at a -1/5, well, that's going to equal some negative number because, again, x will be a -1/5. And then times 2 plus a -1/5 times 5, or 2 minus 1, which is positive. A negative times a positive would be a negative, and so we have our function decreasing on this interval. And now you could choose any number greater than 0, and I would say 1 is a perfect choice. And if you plug that in, you find out your function's actually, your derivative is positive there, so your function must be increasing in that interval. All right, so we're completely done there, with the exception that I should mention our original function is continuous. That's not actually the concern here, but it is continuous, and our derivative exists everywhere. And note that our derivative switches signs from increasing to decreasing at x equals -2/5. That means this is a local max because it went from increasing to decreasing. The derivative exists for all x values from -5 to 5. So I know it's not going to be like a jagged shape. It's actually going to be a nice smooth curve. Also, it goes from decreasing to increasing at 0. So that's a local min. And I'll go ahead and add those points to my table of values, my very small table of values. We already have 0, 0 in there. So now I'm going to plug in -2/5. I'll add that to my table. And you should evaluate your function. I'm going to leave it in exact form, but I'll still evaluate it. So f of -2/5 would be 4/25 e to the -2. So I'll just write that in, 4/25 e to the -2nd power. It's a very small but positive number. That's incredibly important. It's a small but positive number. And by the way, 0 was a local minimum. So I'm going to kind of write that off to the side here, L min. And -2/5, we had a local max. It's always good to kind of make those notes in as many places as possible so that you don't miss out on that information as you go to graph. Now I'll go into the second derivative. And when I do the second derivative, one of the bigger mistakes that can happen is you could try the second derivative on this highlighted piece. I actually made mention when I was factoring that I was not going to, originally going to factor out that x. And the reason why is because when I take its second derivative, I'd rather take the derivative of an exponential times a single polynomial rather than the derivative of 3 objects multiplying. So I am going to rewrite this very quickly as e to the 5x times 2x plus 5x squared. Now, you could totally have left it the other way. It's not that big of a deal. It's just you'd have a triple product rule versus a single. You would have to do the product rule a couple times versus just having to do it once. Although if you're one of my students, you do know how to do a product rule involving 3, 4, 5, or 27 functions. It's actually pretty easy, but let's just go ahead and just do it with that blue ink. So let's take the derivative of that derivative. So we have the second derivative. So f double prime of x. So the derivative of e to the 5x is 5 e to the 5x times the second function, 2x plus 5x squared, plus e to the 5x times the derivative of that polynomial, which is 2 plus 10x. Each of those terms has an e to the 5x in common, so I will factor that out because that's just what we need to do. Factoring is very important. And you'll distribute this 5 into this polynomial here, so you get 10x plus 25x squared, and then write that stuff too. So plus 2 plus 10x. Combine things up, e to the 5x. We have a 25x squared plus 20x plus 2. And that's it. Now, all of this was done so that we could see where the second derivative either doesn't exist or where it's equal to 0. Because it's a product of a polynomial and an exponential function, it always exists. But when does it equal 0? Well, f double prime, whoops, that's not the ink. F double prime is equal to 0 when that polynomial is equal to 0. And this polynomial does not factor. It's not a factorable polynomial. It's a prime polynomial. So we're going to have to go ahead and use the quadratic formula here to solve this equation, which does happen every once in a while. So we'll just go ahead and quickly draw this out. There we go. And this will reduce, not very much, but a little bit, to 2/5 plus or minus. And let's see, this 400 minus 200 is 200. Square root of 200 is 10 root 2 over 50. But 10/50ths is 1/5. So that's root 2 over 5. All right. And let me just check something up here. Oh, that's kind of interesting. Notice, because that negative 2/5 sounded familiar, notice that negative 2/5 is actually a critical number for our original function. In other words, it's where our derivative, first derivative, was 0. So the reason why I checked that was because I'm going to make my number line here, and I'm going to plot them in a relatively similar spot. So the -5, +5 is my domain. And then I need to figure out where negative 2/5 minus a root 2/5 sits, and where a negative 2/5 plus a square root of 2/5 sits. And to be honest with you, if this point right here was 0, then the negative 2/5 minus a root 2 over 5, maybe I'll write it this way, negative 2 minus root 2 all over 5, would sit here, and then a negative 2 plus root 2 over 5 would sit to the left-hand side of 0 because it's still negative. If you needed a calculator to figure that out, then grab a calculator, that's fine. But these are the 2 points that split this interval into 3 pieces. Now we need to check what the signs of the double derivative are over this interval. So f double prime. Now I'll pick a number that's less than negative 2 minus square root of 2 over 5. I am allowed technically to pick -5. So that's what I'm going to do. I'm just going to pick -5. I'm allowed to pick that edge point, so I'm going to pick that edge point. And if you take a look at the function or the double derivative, which is what this is, and if you were to plug in -5, remember the exponential is always positive. So you're going to have 25 times 25 or 625 minus who cares, because that's positive. So I know that in this region right here, it's going to be positive. In other words, our function is concave up in this region. Pick a number between -2/5 minus √2/5 and -2/5 plus √2/5. And obviously a -2/5 sits right smack dab in the center. So let's go ahead and figure out what f double prime at -2/5 is. Again, f double prime is this expression right here. The exponential function is always positive. So imagine plugging in -2/5 into these. You get 25 times 4/25, or in other words, 4. Minus, let's see, 2/5, that's -8 plus 2. So 4 minus 8 plus 2 is still negative. So I know that it's going to be negative. I don't really care what the number is, even though I know it. It's just that it's negative. You should also note it's very attractive to think that these signs here always alternate between plus and minus, but they don't. I think we've already seen an example previously where they didn't. And so it's very important to note that you need to be very careful not assuming that they'll just alternate. The other issue that kind of creeps in here is arithmetic. People always make arithmetic mistakes. In fact, so do I. And so I will often recheck my mathematics as I go through. In fact, I'm mentally doing that as I'm speaking right now. Yes. And let's see, the last interval, I know I can plug 0 in. So I'm going to look at f double prime at 0 because that's super duper easy, because it would be 2 times e to the 0th, or just 2, which is positive. So that's all I care about. I happen to know it's positive, so the curve must be concave up here. Let's see, do we add any numbers that we should have y values for? And the answer to that is yes. We have -2/5 minus √2/5 and -2/5 plus √2/5. Let me use black ink here. So -2/5 minus √2/5 and a -2/5 plus √2/5. This is probably the most annoying thing for students, is just the simple evaluations. It just gets kind of long-winded, and you can see that we're going to plug that into the exponent of an exponential function. And so that's not really going to be a beautiful computation. In these cases, it is nice to have exact answers, but if I am being honest with you, I would say that most of the time I would expect my students to likely grab a calculator just for this computation specifically. So I will go ahead and use a calculator for this computation here. And I went ahead and just did a decimal approximation also for the 4/25 e to the -2, since I had a calculator in hand. This gives you an idea of the scale of our y values. They're very, very, very small, on the order of 1/100th to 1/1000th. So it's very, very small scale. I'm going to over exaggerate this actually when I graph it. So let's see, anything else we need there? Yeah, you know what I'm going to do also? I'm going to go ahead and approximate these values as well, just because it would be nice to have them. And there we have a good kind of idea of the scales. Notice I do 3 digits of accuracy here. And that's not for graphing, but that's just in case we're using an online homework system or something like that. They generally are okay with 3 digits of accuracy. All right, now I go into my graphing mode. I'm going to go ahead and start graphing all of this. Oh, I should mention, I kind of forget every once in a while, but because this function is continuous on its domain, we know that switching between concavities gives us inflection points. So these are inflection points right here. All right, so that all being said, let's go ahead and draw out our f prime and f double prime. And this time, if you notice, I actually graphed both those horizontal bars, the f prime and f double prime bars, and the Cartesian coordinate axes all at the same time. And I had them cross each other. And that's because it gives me an idea of where 0 is on these number lines. All right, let's take a look at our first derivative, f prime. We know we have critical numbers at -2/5 and at 0. So at -2/5, which is a -0.4, I'm going to actually plot -0.4 right about, let me bring up a ruler, and I'm going to do it maybe about here. Let's just say a negative. No, I'm going to do it here. Do a -0.4 right there. And that's going to be a critical value for us. And we know that if I look over here, the derivative goes plus minus plus. So let's go ahead and do that. It's plus, minus, and a plus over here, which means the function's increasing, then decreasing, then increasing. And then for our second, oh, and I should say this is a -0.4, but you know what, I'll mark that actually down below. -0.4, and the y value, by the way, for -0.4 is roughly 0.02. Now, that is not going to be easy if you try to plot 1 here. So let's look at the largest of these numbers, which is actually a 0.022. And I will just say, if that's the largest of the numbers, that'll be the largest value on my y-axis. So like it might be a y value up there. That's where I'm going to probably put 0.22. So let me go ahead and line this up, and maybe I'll try to get a proper scale. Maybe I'll put it right here, actually. So there we go. That point right there is going to be -0.4. Let me see, is that a local max? Yes, it is. So it's a -0.4, comma, 0.22. I have to zoom in for that. -0.4, comma, 0.0, and was it just 10? Yeah, it was 22. And again, that's an approximation. There we go. And let's start now looking at our second derivative. Our second derivative, we have inflection points at that -2/5 minus √2/5 and a -2/5 plus √2/5. We have decimal approximations for those in our table over here. So that'd be a -0.68, or roughly -0.7, and a -0.117. So if this value was at a -0.4, then a -0.67 would probably be around here. And I wanted that in black ink. Whoops. That's what I get for keeping that ruler right next there. And the -1 value is probably, honestly, right around here. Try to get that away. And we know that plus minus plus, when I read that out loud, I'm looking at these signs above this line here. So plus minus plus, I'm just going to write those down. So plus, minus, and plus. That plus, by the way, is this entire length here. I'm just not going to note that, but this means that it's concave up here, it's concave down in this interval, and concave up in that interval. From this point forward, I just need to plot some values. So for example, 0, 0 is a point. So let me go ahead and plot 0, 0. It's right there. Let's see. We already plotted the -0.4, comma, 0.022. We now need to plot the -0.683, comma, 0.1015. Let's see. If I called this height here a 0.2, so that's 2 and some change, and I want 0.015. Is that what it was? Yeah, 0.015. So I know where that's going to be. That's going to be right around here. And I'm using blue. Yes, I am. So roughly right there. So that is the point negative 0.683. Let me write that in here. Negative 0.683, and the y value is 0.015. Let me double check that that was the value. Yep. And then our final point we're plotting is at negative 0.117 and comma 0.008, which is 8 pips up. So I said that was roughly there, and I'll put this point maybe right about here. All right, something like that. And I don't need this ruler anymore, so let me turn it off. And that point again was a negative 0.117 comma 0.008. Now notice how I'm trying to be super accurate here. Now we know that we have some other details that we have to attend to. One thing to note is that at the edges of your domain, if it's a restricted domain like this, but you can include the edges, you should probably write those in your table as well. So I'm going to go ahead and do that. I'm going to say, well, we have these edges at -5 and at +5. So that gives me a 25, because it's x squared, e to the 5x. So that's e to the negative 25th, and 25 e to the positive 25th. Let me just double check that that is correct. Yep, that is correct. Now that is a little bit out of my league right there, because 5 comma 25 times e to the 25th is a massive number. It's like super far off this graph, because notice my y values are not super large here. So that's going to be an issue. It just means that at the edge, when we get to x equals 5, which is roughly, I think the way I have it written out. Oh, no, I did not scale this appropriately because my x values don't go from that to that. Well, you know what? It's totally fine. As we go this direction, it's going to go up to infinity, or look like it will. We just won't have the graph from -5 to 5. That's my fault. Sorry about that. And then at x equals -5, our y value should be, and let me grab a calculator here, 25 divided by e to the 25th. I'm just typing this into Desmos here. Roughly 0. It's still positive, but just roughly 0. All right, so let's go ahead and mimic that situation. It's going to tend to 0 on this side. And it's going to be concave up and increasing. So let's go ahead and do that. It's concave up and increasing. It's going to tend to 0 as it tends to x equals -5. One thing I completely forgot when I drew this was the domain of the function. So I should have had this wide enough to include 5 and -5, but actually kind of having it zoomed in like this is nice for graphing purposes anyway. So I hope you would agree that this is concave up and it's increasing, but then it switches to concave down after that moment right there. That's an inflection point. So the inflection point. We get to our local maximum, and now it's going to switch to decreasing and still be concave down. Something like that. And we get to another inflection point, because that's what these are, right here and here. And we switch to concave up. We're still decreasing though. And remember, I should have plotted it here, but remember that between, I think that's right. Yeah. X equals 0 was a critical number for the function, so its derivative is 0 at 0. And so we'll have a switch from decreasing to increasing at that moment. But right now we're decreasing but concave up. Try to do that appropriately. I think that's pretty good. This is an inflection point right there. And then it continues to be concave up, but it starts to increase from that point forward. And by the way, it will increase very rapidly from that point forward, because by the time it gets to x equals 5, it's something your calculator likely cannot compute. In fact, let me just see if Desmos can even compute this. 25 times e to the 25th is, yeah, it's a massive number. On the order of 1 trillion. So if you think of it in terms of the y values that are represented here, it is going to be far beyond what this can achieve. But in the long run, had we graphed it in a -5 to 5 scale, it probably would have still looked really wild. Something maybe like this. Yeah, it's something like that. But I like the zoomed in version anyway. It's a very nice version of it. And we really were allowed to plot all the values appropriately and get a really clean looking graph from this. So I dig it. So, all right, we're done with this graph. The next video will be the last graph that we will do in this series.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.